Good morning, everyone. I'm going to give it another minute or two to see who pops in, and then I'll go ahead and get started. Okay, we'll go ahead and get started here. A couple of admin um, things to sort of start things off. You guys can use the chat over on the right hand side of the screen in order to talk amongst yourselves. Questions for me, go over to the far right hand side that says Q&A, and that's where I will read and answer questions. You can type in questions at any time, and I will be happy to read them and answer them as we go through the presentation. So Artemis Propulsion System, how the United States gets back to the moon. This is a rather interesting rocket. I'm going to talk about the propulsion systems. In terms of full disclosure, I've worked at both of the companies that are making the rockets on this launch vehicle. I used to work at ATK, which then became Orbital ATK, which now is Northrop Grumman, and they'll manufacture the solid rocket boosters and part of the launch Abort System solid rocket motors. And I currently work at Aerojet Rocketdyne as a director of business development. And Aerojet makes the RS25 4 engines down at the aft end, the liquid rocket motors for the exploration upper stage, and one of the solid rocket motors on the abort system as well. So there's quite a few bits of rockets on this thing when it's all said and done, and it's a pretty cool system. In addition to kind of the genesis is, I will tell you that I've made plans to go down and see the first launch, because I don't think that perhaps outside of maybe the Saturn V, the chance to see this thing fly is truly going to be spectacular. I've seen the shuttle go a number of times. I was a little too young to see Saturn V go, but this is going to be like a combination of both of those, and it should be pretty spectacular. The only caveat I'll put to that is I'm not planning on just jumping down when they announce the launch date and coming home the day after. As almost with all new complex systems, there will be some bugs to be worked out, and so I'm going to probably take a Florida vacation. There's no official date yet. They really are talking about March, but I don't know if that's really firm yet, given they had a problem on one of the engine controllers and having to replace it. And apparently it is quite a challenge to physically go in and replace it. So my guess is it'll go this summer when it's really hot and uncomfortable in Florida. That it'll wait to that. March would be beautiful. June is pretty oppressive, but I suspect that's where it's going to go. So let's talk about SLS, or Space Launch System overview. And SLS in alone is kind of an interesting name, because it's nicknamed in the Washington, D.C. circles as the Senate Launch System, because it largely has come about because of Senators Kay Bailey Hutchinson, that used to be the senator from Texas, and the senator from Alabama, who was very, very powerful in the Senate, Richard Shelby. So the joke was they kind of kept it going and kept the budget for it in place. And as expensive as it is, it's always had a target on its back. However, it really is a super heavy lift launch vehicle that will let us go beyond Earth orbit, and there is nothing like that. You'll see it coming up how it compares to Falcon 9 Heavy and some of the other stuff, but it really is a huge lift capability, and it's going to be quite the launch vehicle when it's all said and done. So it's taller than the Statue of Liberty, and it's about 15% bigger on the first stage than what the Saturn V was. So it's truly going to be spectacular to see it fly. So they're just about ready to get the Artemis 1 mission going, and that's going to send an unmanned Orion spacecraft around the moon and then come back. That'll demonstrate the performance of the SLS, the Orion, and the exploration ground systems prior to a crewed flight. And probably the most interesting aspect of the Artemis 1 flight will be is it'll let them test the heat shields on the capsule, on the Orion capsule, at a very realistic velocity. Slingshotting coming from the moon provides a lot higher heating as they re-enter the atmosphere than it would simply be a deorbit from Earth orbit. So that's going to be interesting. And then Artemis 2 is planned to send astronauts to the moon. You'll see a little bit later the overall plan, but fabrication for Artemis 2, 3, and 4 are actually well underway, and most of the propulsion for Artemis 2 and 3 have been delivered. So it's a pretty exciting time coming up when it's all said and done. So this slide shows an overview of the propulsion system itself, and I'm going to start from the bottom. And it shows the RS25 engines. There's 4 of them. RS25 is basically adapted from what the space shuttle main engines were, but these are designed for a single use. And we'll talk a little bit more about the origins coming up, but that's that. Then you'll see there's 2 solid rocket boosters. Those are 5-segment solid rocket boosters, so they're bigger than the ones that flew on the shuttle. There's a main core tank, orange stage in the center that's liquid oxygen, liquid hydrogen. And then up above, there's 4 RL-10 engines. Those are also made by Aerojet Rocketdyne. Those have more than 500 launches into orbit as a heritage on them. And the interesting thing is those have been upgraded in recent years to include a number of 3D printed parts that has brought the cost down significantly and made it much quicker and easier to manufacture. So it's an interesting evolution of what is basically a 1960s engine when it's all said and done, adapted for the future. And then in the launch abort system, you will see some more U.S. engines. There is also a service module engine similar to what the service module on Apollo was, and that's actually being made by the European Space Agency, and I'll talk a little bit about that. But this is quite an impressive rocket, and has a number of sophisticated technologies on it. And as a note, these technologies are thoroughly vetted because this is going to be a man-rated vehicle. So on the top, this is how they plan to evolve the configurations as they go through time. So the Block 1 in the crew version is basically got what they call the exploration upper stage, which is the 4 RL-10 setups, and that will eventually evolve into where they use the RS-25's new builds. There were 14 to 16 RS-25s remaining from the shuttle program. Well, there were 16. We had to build 2 new ones to fill out the 4th flight set. So after the first 4 flights, it's all new RS-25 builds, and those are in fabrication at Aerojet Rocketry right now. But the first 4 flight sets are basically all done. And when you've seen the testing, at in Louisiana for the RS25s, the engines themselves. That's been focused on mostly validating the new build RS25s. And then the other thing is there were 8 sets of steel cases remaining for the 5-segment RSRM. Once they get through the first 8 sets, they will use what they call the bowl, and you'll see some more details on that. But those will be basically upgraded solid rocket motors for the strap-ons as well. And when they get to that configuration, that's basically the sustainable configuration going, where everything will be thoroughly modernized and used going forward. Then there's also a cargo version that will start with a Delta IV heavy fairing, and that will provide a large amount of cargo. However, eventually, what they want to do is go to a bigger full diameter fairing on the cargo, and then eventually stretch that once they have the lift capability of the Bowl solid rocket motors. Then it will give them the capability to stretch that fairing and go even more. So yeah, it's interesting to see how they've gone it. I know, Bob, you've asked in the box, is there a chance that J2X development will go into again? The answer is yeah. We really think there's a good possibility, and we're working on that as we go forward. But we pretty much have mothballed most of that work at this particular point in time. But we think that J2X will come back probably after the first 1 or 2 flights. And Ed, I see you asked how many SLS vehicles are funded to be finished and flown at this time. There's long lead funding out for the first 5 vehicles. Most of the components are finished for the first 4 vehicles, but NASA works on a year-to-year basis, and so the funding for the flights is not necessarily firm at this particular time. So that's how that answers. And then just going back, so on the Block 1 configuration, Bob, there are actually 4 RL10s, I believe, on the Block 1 version as well. But I'll have to check that in order to make sure. These liquid drippy rockets I don't do nearly as good as the solid stuff. So this gives you kind of an overview of what the RS25 engines are, and these are all previously flown on the shuttle. What's interesting is they've actually picked one that has 12 flights on it. So it first flew on STS 89 in 1998. I'm sure a couple of you listening were not born then. This engine also flew on John Glenn's last flight, STS 95. So it's interesting workhorse that is part of this core stage. And of course, these are not LOX kerosene like you see in most of the other launch vehicles, but this is liquid oxygen and liquid hydrogen. So these are incredibly powerful, incredibly efficient liquid engine rockets, and basically, the best, most optimized design that you can get out there. Liquid hydrogen is tricky to deal with, but once you harness its power, it's incredibly efficient and incredibly powerful. And those 4 engines give you about 2 million pounds of thrust. If I told you before, it's like a little bit over 8 million total, so you'll get an idea what the solids do. But like I say, I mean, so the first mission here will use 4 of the liquid rocket engines, the RS25s. And then what's new for SLS is that they did increase the thrust levels when they were using them in a reusable configuration. they they took a little more care because they wanted to bring them back and reuse them. Since these are now kind of going to go to single use, they're going to let them run at a higher thrust level, simply because they don't have to worry about reusability. And then the other thing is they updated the engine controllers, with all new digital electronics and everything like that. Because again, these things were originally designed in the 70s and started flying in the 80s, and so it just begged for an upgraded, more robust engine controller. And so those are also fabricated at Aerojet Rocketdyne, and that gives a considerably more control power and data feedback over the old system. And so it's an interesting engine. It's a turbo pump engine. So they literally pump, the liquid hydrogen and liquid oxygen into the combustion chamber, and gives you a very fine control of the ratios that are introduced into the combustion chamber. And the operating temperature is amazing. It's the liquid hydrogen is at minus 423 degrees Fahrenheit. When everything burns, that's at 6,000 degrees Fahrenheit. So it's quite a thermal shock, and quite a robust system to take that vast range of temperatures. We fabricate those at our Aerojet Rocketdyne facility in Canoga Park, California. They then go to Mississippi to be assembled and tested in the NASA facility down there. They then go to Michoud, Louisiana, to be integrated into the core stage that Boeing is building. Then they are loaded on a barge and transported to Florida, and that's where they're taken off the barge and then sent to the launch pad. So the other thing is being liquids, they go for a long time, unlike most of the rockets that we're used to. It's about an 8.5 minute burn. That's really a long time to hold your breath. It's during the test of one of these things. I mean, it's pretty impressive, and in that, but 8.5 minutes is a long time. And as I talked about, it provides 2 million of the 8.8 million pounds of maximum thrust. However, the solids are really only good for about 2 minutes of the initial thrust. So these continue to cook for another 6.5 seconds after the solids separate. They're really works of art. They're fantastic. They're fantastic engines when it's all said and done. And as you can tell by the picture on the right, lots of detailed wiring, lots of harnesses, lots of stuff. So here are the actual 4 that were integrated into Artemis 1, just to give you an idea of the size compared to a person. Like I say, pretty cool. I like the covers with the name on it, but look at all the stuff that it's covering up on the sides even. I mean, it's a complex engine, there's no doubt about it. Now the solid rocket boosters, and these we're a little more familiar with. So it's interesting because one of the things that they've done is the old shuttle motors used a binder called P-band, which is a very epoxy-like binder, something similar to what the original Enerjets were using, a little more refined. But most everything today uses HTPB, and all your Aerotech reloads and motors use HTPB. And these now have been upgraded to use an HTPB propellant in them. Part of the reason they didn't switch before is the system was man-rated for the other ones. But HTPB really was a 1960s propellant formulation for the most part. The problem, or the P-band was, the HTPB is more modernized. However, the P-band is kind of like an epoxy-based system, and it's very hard. I mean, you literally could take a reload grain was made out of it, you could take it and slam it on the on your desk, and it would sound like a rock or a brick. The HTPB ones, as you guys all know, is a little bit softer and more has the consistency of a pencil eraser. Well, it becomes very important that you get the strength and the dynamics of that correctly, particularly in a big segmented motor like this. And literally, if you make the HTPB propellant too soft, you can have chunks of it rip off, or you can have it move. The what was Hercules is now ATK. Northrop Grumman guys learned that the hard way when they scaled up the Titan IV strap-ons and built the first one out of HTPB and had it blow up at the test stand out at Edwards Air Force Base. And part of that was the propellant dome collapsed, tore off a big chunk at the head end because it was all flexible. So there's an art to putting this together. It wasn't just a straightforward one-for-one swap. But the result is you get a much more robust propellant that can withstand bigger temperature changes, and you do get more performance out of it when it's all said and done. So it's pretty neat. Again, kind of like our reloads, these actually have spacers on the back ends of segments like 1, 2, 3, 4. You can see they actually kind of have a grain spacer that lets it move, lets the grains expand and move within the case itself. And so, like I say, pretty neat motors when it's all said and done. So the other thing is these things are really something to see. Here's a picture of a static test out at Promontory. The tests are open to the public, and for those of you making travel plans, theoretically after first Artemis 1 launches in March, April, May, there's a static test of another 5-segment one of these scheduled for June in Promontory, Utah. So if you in a way, seeing the static test of this is better than seeing a launch, because the motors fly away from you in 2 minutes and you're gone, a little specks in the sky. This thing sits there, you're a mile and a half away in the public viewing area, and it goes and goes and goes. And about a minute into it, you can't believe it's still going and has another minute left to go. It's very impressive. So if you're looking for a unique a vacation opportunity, coming to Utah in June probably is a rather interesting thing, and you can catch this as well. So this is the bowl design, and what it really is it's going to go. The big thing is it's going to go away from the steel cases, and it's going to go to a 5-segment composite case, and that will provide a lighter case than what the steel were, which gives it additional propellant. As I said, they're going to integrate HTP propellant into this motor. They're going to reshape the grain a little bit to match what optimizes it for the flight profile of SLS. Shuttle is a little bit different, and so they actually have the grain configured in a way that it sort of down throttles as it goes through max Q. So, and then so that they don't overstress the airframe. These are when you have a steel case, you get the piece of steel in, and then you put the internal insulation in by going in with big sheets and basically bonding it to the inside and then vacuum bagging it. The way that these are made is they have a steel mandrel that's very similar to what Tim Van Milligan does for a lot of his competition models. They'll have a steel mandrel. They'll actually strip wind the rubber over the mandrel, trim it, machine it to size, and then overwind the carbon fiber epoxy case, and then put that in the oven and cure it. And then they'll go in and unbolt the mandrel from inside and remove it. And they have the insulation and the case all integrally bonded and cured at the same time. So it's the nice thing is it's a pretty efficient way to do things, and you don't have any problems with unbonds in the insulation or impurities or anything like that. And so it's it's a pretty good deal when it's all said and done in terms of improved quality. I'm going to get in trouble here, messing around. So there we go. And it has a more efficient nozzle on it as well. So they made some changes in the aft assembly that are pretty minor, but they did it externally mount. When you see BSMs, those are booster separation motors. Those are also made by ATK, and those are just designed to push the booster away at separation. And then they made some basically changes that were more optimized for SLS for attach points, and some modifications for that. And then integrated a new systems tunnel. There's a new destruct charge, and a little bit better lightning protection, because we do have lightning storms down at the Cape. And so when you had an all steel case, the path for the charge was pretty straightforward. Composite cases, you have to provide a clear grounding path, since the carbon fiber epoxy case is not electrically conductive. So that's what the new motors are going to look like, and that's what they're actually testing up at Promontory. You'll get a chance to see it. So it's a pretty cool thing. And then the other thing is between the differences of improving the propellant and lightening the case, it'll give 3 to 7 additional metric tons of payload to TLI. This is the exploration upper stage. So the EUS has 4. On the interim is cryogenic propulsion stage. It has 1. So Bob, I think that answered your question. Is right now there's 1, and I'll actually show you a picture. And you can see that they're about 25,000 pounds per RL10 engine. So, and again, this is a liquid oxygen, liquid hydrogen engine. So it's very efficient, and provides a lot of capability in a relatively small package. When they go to the 4, they get about 40% more payload capacity to the moon, and it's a pretty will give you a total of about 38 metric tons to the moon. So that realistically is enough to do something useful. And there is the interim cryogenic propulsion stage. This will be the one that will fly on Artemis 1. Launch abort system. So kind of going back to the days of Apollo, and the concept was pretty much adapted from what we did on Apollo. There's 3 rocket motors on the launch abort system. So the one starting from the bottom up, there's a fairing assembly that covers the whole Orion crew module, and so that's designed to move it away. It also provides any sort of protection to the capsule on ascent, that should anything be impacted or like that, the fairing assembly takes the loads and takes the brunt of it, and then you don't have to worry about any damage to the capsule, particularly exposing it to anything that you might worry about on reentry. So it's a pretty impressive piece, and then it adapts to the overall abort system motors. So the bottom motor is the abort motor, and that's the one that would actually pull away the capsule if there was a determination of a problem on the booster. There's also an attitude control motor in the nose, and that's a solid propellant gas generator with 8 valves that turn around and basically steer the capsule. That will make sure that it flies away clear of the booster in case of a problem, and gets it away. And then there's a jettison motor, and the jettison motor is the one that actually pulls away the launch abort system from the crew module. And on a nominal flight, those are the ones that will actually work. So, and then in a case of an abort, those pull this whole structure away so that the parachutes can open. Launch abort systems rocket motor. So here's a chance to kind of look at things as they were integrated. So the if you'll go back. So the jettison motor is the one in front, and that's the one that will, pull the whole structure away from the capsule. And the one at the right is the abort um, motor. So this picture shows it. I'll talk, I think, a little bit more. Let's see. Yeah, this is cool. So the neat thing about this is this has got turnaround nozzles, and so what it does is the nozzles, the four gases actually make a U-turn from the motor case and then come out. So it's or you can consider it like a tractor type rocket motor. And it can be done. It's just a little tricky. The picture on the right shows a static test that's actually up at Promontory. Um, and so it's a, like I say, pretty unique setup. So what they do at Promontory to test that one is they turn it upside down and then test it in that particular configuration. So it's an interesting motor. All of these on the solids, they do have they do extensive testing, but obviously unlike the liquids, they can't retest them. So they make prototypes, will fire them, and then send the actual flight motors down to the Cape. So there's no kind of pre-testing like what you can do. The only testing on the solid you can do is to fire it. So the attitude control motors, and this is not a liquid, but it's a solid propellant with high temperature proportional valves. And this is similar to technology that's been used on a lot of the missile defense programs and is still evolving, but it literally means that you can throttle with solid propellant motors. And this one provides a high impulse of energy that lets the nose tip over and go any particular direction quickly. Very important for an abort system. It's fully redundant and is man rated, and so it's an interesting little package. But it has very high temperature metal valves in there that allow for the proportional steering. So this is not used for any sort of flight control, Robin. You see you're asking this. It's not used for flight control. It's strictly used for steering the capsule in case of an emergency. So it's a pretty good deal when it's all said and done, because it works quick, and obviously in case of an emergency, that's what you want to work quickly. So, and then this is the jettison motor. This is what pulls the tower away. This is made by Aerojet Rocketdyne, and it's the only motor of the escape system to work on all the mission scenarios. And it's about 40,000 pounds of thrust. And again, it's got canted nozzles on it. Now, it doesn't have the turnaround nozzles that the main abort motor does, but it has 4 canted nozzles. There's a little bit of, you lose a little bit of thrust efficiency when you do it that way, but it's the only way that makes sense to keep the flames out of the way and from burning everything down below. So pretty cool to see that motor, and it's a relatively short burn time as well, so it gets up and goes. And the picture at the right is a test at Redstone Test Center in Huntsville, Alabama. The European Service Module propulsion is a liquid system that basically operates similar to what the service module did in Apollo. And this is put together by the European Space Agency and supplied as part of the international effort for SLS. Theoretically, I laugh. I didn't get a chance to update the chart for the first non-crewed Artemis test flight in 2021. Obviously, that didn't happen, but this has been delivered and is ready to go, and this will be active and go when it goes to the moon, theoretically in 2024. Probably will be closer to 25 or 26, but things are stacking up nicely after the first launch to get everything done. And this is built by Airbus, okay, and it has 24 reaction control system thrusters and 8 auxiliary engines for maneuverability, and then it has uh, a large OMSE for large translational burns. So it gives it the capsule pretty much complete capability. Picture on the right gives you an idea of the entire back end of the service module and where the propulsion units are located. So how big are we talking? I mean, everybody has seen Falcon 9, which is really the biggest one that we've seen in recent times. This is much bigger than a Falcon 9. And the picture on the right shows you the difference on the potential launch pad. This is also a little bit bigger than the Saturn V, as I said before, considerably more powerful than a Saturn V. It's also much bigger than the Blue Origin New Glenn on the ULA Delta IV Heavy on Vulcan or the Space Shuttle. So when you hear people talking about Blue Glenn or New Glenn or Falcon 9 Heavy matching the capabilities of what SLS can do, that's not really capable. The specs on the Starship that SpaceX haven't really settled out, but this will be probably bigger than Starship as well. But this is a big rocket. This is going to be incredible to go see fly, and it's going to provide an unparalleled amount of cargo to orbit. So how big are we talking in NER terms? So I went ahead and converted these in order to what our normal engine configuration is, and to give you an idea. And the RS25s each are double E motors, 1.8 million -Ps. The 5-segment RSRMs are double E's, 10 million -Ps. So if you want to order one for your I assume that anybody who puts stuff into orbit is a level 5, right? So this would be a good start for something for level 5. But in all honesty, that EE motor by itself is not big enough to put something into orbit because the burn time is too short. And unless I hadn't run the calculations, but it's a maybe you can put a couple of pounds, but it's not optimized for getting things into orbit. But it'd be a hell of a flight. There's no doubt about it. So the total stage one that would get you to orbit is an HH motor. That's roughly about an HH 12 million. That's impressive. The stage 2 ICPS is a Z motor. When they go to the cluster of 4, it becomes a CC motor. The launch abort motor is a V motor, as in vector, and the jettison motor is an R motor. So an R196, well, that's almost in the realm of some of the stuff that has been flown out at Black Rock. So that one would be an interesting one. If you're interested in buying one, come talk to me. You probably can't afford it, but I'll at least get you a price. So that kind of wraps up most of what I had on this discussion. Let me go through and just work a couple of questions. So Bob Morstead had asked, are the pressure oscillations still a concern for the SRBs? And the answer is no. There's been a lot of mitigation in how they've gone and done it. And then the other thing is there was a lot of worry when they went and flew the Ares 1X. They got a lot of good data that also answered a lot of the questions, and they didn't see nearly as big a problem as what they had theorized they would with getting some actual flight data. You get some information on the static test, but also you get quite a bit of information on a real flight test. And so they think that those issues are minimized. Now, the one thing is I used to work for Ron Graby, who was a space shuttle astronaut. He flew 2 flights before the Challenger accident and 2 flights after the Challenger accident. And he said the first 2 flights that they flew with their helmets open in the capsule, and then the second 2 flights they flew in fully pressurized suits. And he said that on liftoff, you can feel the liquids start to burn up, and the liquids are very smooth. But when the solids ignite, it's like a train wreck. And he says it just shakes the hell out of everything, and everything rattles, and everything, noise and everything like that. And so he said the strangest transition is when they were flying in the full suits and everything like that. There was no sound. They said they could still feel all the vibration and everything like that, and it shook like a son of a gun, but no sound whatsoever. So the solids are very violent in terms of vibrations, and then he said when the solids burned out, it was like a smooth car ride. He said no problems at all. So there are different dynamics to the motors and that, but they do believe that they've mitigated a lot of it. But the solids, when they're firing, it's a rough ride. Let's see. Paul Kinzer asked, when do we find out the schedule for the SLS booster? The big thing is watch the NASA test site. They have not finalized the date for the test yet. But I was told by the PR person at Northrop Grumman that in April they probably will finalize the date. And it's interesting because so they will condition these things to a target temperature. They'll either have a nominal temperature, which in the solid rocket business is 70 degrees Fahrenheit, or they will test at cold, which I think is minus 30, and then they will also test maybe at hot at 90. So what they'll do though is they'll get this thing all assembled on the stand, and they have a big building on rails that rolls over it, and then they proceed to condition it to a temperature, and it takes like a month for the motor grain temperature to get down to the desired temperature level. So they'll know more than a month in advance when they're going to go like that. So, but like I say, watch in April. They said they probably will announce. Watch NASA, or you can watch Northrop Grumman's site, and they will announce the date. And the cool thing is the guys up there are really good. They really know what they're doing. I had a test up there that I was running, and in February we went and said we'll be testing in November, and they said that's fine. It'll be on the Thursday before Thanksgiving, and we'll test at 1:00 in the afternoon. It's like, what? No, they have their test set up, and they know their procedures and everything like that. That they would set the test up for us on Monday, and they had their test countdowns and data acquisition checks and everything on Tuesday and Wednesday, and then they were set to test Thursday at 1:00, and then that would give them Friday to tear everything down, and then they would go in on the next thing. And we actually got to November. We didn't hit the Thursday date because of some technical problems on the equipment that we provided, so it took us a couple of days to fix that. But we tested the following Tuesday at 1:00, and pretty incredible. So the good thing is probably unlike a launch, unless they have bad prevailing winds, this will probably go off on time. And bad prevailing winds is they never used to worry too much about the cloud that comes out of the exhaust. It's got a lot of hydrochloric that can mix with water in the air and become a hydrochloric acid. But they did have one where there was a cloud overhead, and they did get lots of acid, and the farm that was about 5 miles downrange got hammered with it and destroyed all the cars, and they had to go back and pay a significant amount of remediation. So now they watch the weather a little closer with that, because the thing of it is, when that burns, it sends a cloud of exhaust. It looks like about a mile up in the air. It's really, really impressive. And so weather conditions would be the biggest reason why you might not a see a test. But generally, they have things worked out in pretty good shape. So, and then Pat Fitzpatrick said, have the SRB field joints evolved since STS? No, those are pretty much the same ones. There are some minor accommodations because of the way that the carbon fiber cases expand a little bit differently than what the steel ones do, and so there's some changes they made dimensionally inside the field joints to accommodate that. But basically, the design is the same one that's been flight proven on the shuttle when it's all said and done. So that's that kind of wraps things up. Other questions? You want to put them in the chat or in the Q&A? That would be fine. So if you have questions in the future, feel free to contact me through the North Coast Rocketry website. Be happy to answer anything relative to this, and look forward to probably seeing some of you down to the Cape when this thing flies sometime this year. Appreciate it. I'll give you back some of your time. Thanks, everybody.